Okay. Let's talk about the thermodynamics. What is meant by thermodynamics? A branch which deals with heat, work, and temperature and their relationship. Relationship to energy, physical properties of matter. A branch which deals upon the heat, work, temperature, respectively. Basically, JEE and NEET, both syllabus same. You can follow this lecture too. Coming to the ideal gas equation, what is meant by ideal gas or real gas? Here there is no force of attraction. Here we can see intermolecular forces. Okay. What is ideal gas equation? PV is equals to nRT, which gives a relationship for both temperature and pressure. Let us do a problem which is related to the JEE. Okay. Initially a gas. Okay. Let us solve afterwards. Let's move on to the new topic. What is degree of freedom? Do someone know about this? Let me tell you about this. The number of ways or modes in which a molecule, let me erase it. Okay, give me some time, I will fix this. The number of ways or mode in which a molecule can acquire kinetic energy, I mean internal energy, is known as degree of freedom. Basically, degree of freedom is of four types: monoatomic, diatomic, polyatomic, in linear. Poly, non-linear. Okay. Okay. Let's talk about the monoatomic. Monoatomic gas. Let me give me a color. Let me take a gas of a single molecule with a nucleus which have a translation motion of x-axis, sorry, y-axis, x-axis, and z-axis. What is meant by a monoatomic gas? Let me tell with the example. The examples of monoatomic gas are helium, argon, any noble gases. Monoatom, which have single molecules. The translation modes of monoatomic gases is 3. I mean of mvh square, of mvy square, of mvz square. Let me erase this all. Sorry for the voice break. uh, okay. Let us talk about the degree of freedom of monoatomic gas is 3. Okay, let me give me with a new color. The degree of freedom of monoatomic gas is 3. Okay, let me change the color. Okay. Coming to the atomic gas. Diatomic gas, basically, the examples of diatomic gases are oxygen, hydrogen, nitrogen. Uh, O2, O2, H2, N. The examples. Let me take an two diatomic molecules with a nucleus which have y-axis, which has x-axis, which has z-axis. We all know that kinetic energy of y-axis is of I y omega square. Since moment of inertia we have learned in our previous class. The moment of inertia is of I omega square for a rotational modes. Coming to the derivation, kinetic energy of y-axis is of omega square into Iy. Okay, let us take an example of diatomic molecules which have a nucleus y-axis, x-axis and z-axis. The full atom mass lies in the nucleus. We all know that. In an atom, 99.9999% fill its space. Only that not 1% will be filled. Okay. Point mass of a nucleus is mr square. Okay, one atom is mr square. And the atom nucleus mr square. If the is substituting the I y I z. Re, dengue kencet. Oke. Convert कर 2 minutes. Oh, okay. Let us continue. Sorry. Kinetic energy of Yx. Okay, it's not visible. I will continue with another color, darkest color. Okay. Kinetic energy of an y-axis is of Iy omega square is of 2mr square into omega square. Mr square plus mr square 2 square. Okay, let me not derive with this. Let me erase this. Okay. Kinetic energy of z-axis similar to this of Iz omega square is equals to of 2mr square into omega square. But kinetic energy of x-axis is 0 since the reason is a atom which nucleus lies in the axis of x-axis. We all know that. Okay, I mean, do you understand? Always nucleus here, sorry, here nucleus lies on the x-axis. Therefore, Ix is equals to 0 of Ix into omega square, which tends to okay, let me erase this. Tends to 0, which gives me 0. Okay, let me give me another color. Okay, therefore the translation modes, the rotational modes, the translation modes are 3: Vx, Vy, Vj. The rotational modes are only 2. Here we can't move in this case. Okay, the rotational modes are 2. Here we will introduce another one, vibrational modes. Do it. Vibrational modes. vibrational modes in diatomic gas. There are two conditions. One is at high temperature and there is at ordinary or normal temperature. Okay, let us take in diatomic molecules. Okay. Okay. Let me give me another color which you can be easily visualized. Okay, let me take in two diatomic molecules which have a nucleus only. Let us take an hypothetical spring in this between molecules. Here we have an Okay, sorry for the inconvenience caused. With these two diatomic molecules which have of kx square plus of mv square, like kinetic energy and potential energy. These two energies can exchange like this. We can say this. At high temperature there are two at high temperature we have two modes and at ordinary we have zero. Therefore let me give me with another therefore F diatomic at ordinary temperature at high temperature is 5 and we get 7 here. Okay, let us go to the other one which deals, okay, let me take this color, okay, and add in thickness like this. Let me go polyatomic linear. Example CO. Let me take in colors. Sorry for the inconvenience causing. Okay. Taking example like CO2, let me give an example visualization, which is a diatomic molecule cargo. Let me take an polyatomic linear which having a nucleus Vy x of V axis and Z axis. There are the translation modes. Translation modes are 3 and rotational modes are 2. Let me go to the polyatomic polyatomic non-linear gas. The example of polyatomic gas is, let us take CH4, ammonia, and water molecule, and so on. Let us take in polyatomic non-linear gas molecule, which is like in this. Sorry for the diagrams. Y-axis, x-axis, and z-axis. Okay. Let us take the translation modes 3, the rotational modes also 3. Since here we have 2, the reason we all know that nucleus, here we can move, but here the Ix is equals to 0. Here it was far away from the nucleus, we can rotate it here. Therefore Ix is not equals to 0. Therefore degree of freedom of polyatomic is 5 for linear and 7 for non-linear. Okay, let us go to the law of equipartition energy. Sorry. A small calculation mistake here. The polyatomic non-linear molecule is 7. No, I was calculated wrong. 6. Okay. Okay, I'm ready. Start చేస్తున్నా. Bye. Okay, coming to the law of party equipartition. The law of equipartition states that the average kinetic energy of each molecule per degree of freedom is equal and same to of Boltzmann. Okay, we all know that Kb is known as Boltzmann constant. Kb equals to R upon Na. R is universal gas constant and Na. Hello? కనబడుతుంది ఇప్పుడు కనబడుతుందా చూడు రాస్తుంది
Okay. Purchase na?
The the average kinetic energy of each molecule per degree of freedom is same and equal to of kT. We know that kb is equals to Boltzmann constant. kb is equals to r upon Na. R is universal gas constant. Na Avogadro number. Okay. T is absolute temperature. That is the average kinetic energy per degree of freedom is equals to of kBT as we discussed here. Okay, let me give you with another color. Let us take blue. Average kinetic energy per molecule yet degree of freedom is equals to of kT over 2. The total kinetic energy of n molecule, simply keeping n in the above equation, gives us the total kinetic energy of n molecule. Okay, let us discuss about total number of kinetic energy of 1 mole gas is how much. Let us tell us I will elaborate it neatly. Kindly concentrate here. We all know that kinetic energy sorry I will erase. U equals to Na into K F T by 2. We know that the Boltzmann constant Kb equals to R upon Na as we discussed here too. Okay. Okay. Then I can write Na into K like R, since Kb into Na gives R, since therefore R into F into T by 2 gives me the total kinetic energy of 1 mole of gas. Okay, let me give me with another color. Total kinetic energy of n moles. Very importantly, U equals to NFRT over 2. Very important formula. Okay, since internal energy increases, temperature also increases. As we know that and landing states of matter, Vrms equals to root over 3RT by 2. Since Vrms increases, here T also increases. Very important. Okay, let us go to the table itself. Let me take a okay, let me take a time to understand very deeply to this chapter. Since 2 to 1 question will be given in the JEE and 1 and 2 to 3 questions in NEET. Let me give to this gas. Degree of freedom and internal energy, molar specific heat at constant pressure, at constant volume, and degree of freedom, translation plus rotational plus vibrational plus U. We know that NFRT over 2. Okay, let me give me this here. Internal energy and CV molar capacity, molar heat capacity of at constant volume, at constant pressure, and okay, let me allot it very elaborately. Okay, monoatomic, diatomic, polyatomic, linear, polyatomic non-linear. We know that degree of freedom of monoatomic gases is 3 plus 0 is 3. For the diatomic molecules we have 2. At normal we get 5. At high temperature we get 7. For the polyatomic molecules 5, 3 rotational, 2 rotational and 3 translation. Here 3 rotational plus 3 translation plus 3 rotational gives rise to, we get 6 degree of freedom. We know that U equals to NFRT over 2. Substituting F in the values of degree of freedom, we get 3 nRT over 2 5 nRT by 2. Okay, let me erase it. Seven nRT by 2 and 5 nRT by 2. I am not doing anything here. I am just applying this here in the F place, and 6 nRT over 2. We will discuss these three after molar heat capacity when we discuss about the calorimeter. Okay, let us go to the internal energy. The name itself tells about this. Thermodynamics is nothing but the day-to-day life. From the internal energy is nothing but sum of all energies, which gives us internal energy is equals to kinetic energy plus potential energy. Ke plus P. Ke is NFRT over 2. The potential energy is 0. The reason behind this is the simplest reason. There's no intermolecular forces of attraction between the molecules. Simple. Therefore, internal energy is equals to NFRT by 2. Okay. The total internal of gas depends upon temperature only. it's independent of pressure and volume. Therefore, change in internal energy is NF or delta T over 2. Many times it was asked in JEE. Okay, this is the basic idea of thermal internal energy. Let us go to the thermodynamic state. Let me give me another color which suits. There is nothing but okay, very light. Let me choose a darkest color. Okay, thermodynamic variables. What are the thermodynamic variables? Let us discuss. Pressure, volume, and temperature. This denotes the thermodynamic variables. Pressure, volume, temperature. These are variables collectively represent thermodynamic state of any gas. What is meant by thermodynamic state? First, understand about what is meant by thermodynamic variables. The collection of thermodynamic variables is known as thermodynamic state. Okay, let us go to the other one. Okay, let me choose this color. Okay, coming to the state function and path function, let us give us an example. What is meant by distance? What is meant by displacement? Let us know about this first, going on to the state and path. Let us take in 2 points, A and B. Let us give a path like this, and there's something this path to reach B. Okay, let me choose another color to the best visualization. The distance is called, the distance is path difference. The displacement is path independent. Distance is path dependent. Displacement is path independent. It can be this or it can be this to reach ultimately the B. Okay, let me erase this. Coming to the state function, the thermodynamic parameter which only depend on initial and final thermodynamic state.
హలో
చెప్పు, ఇప్పుడు కనబడుతుందా? చెప్పు ఇప్పుడు. ఓకే, ఓకే కనబడుతుంది కదా? ఓకేనా? ఓకే. ది thermodynamic parameter which only depends on initial and final thermodynamic state. And clear, I am telling clearly, not on the thermodynamic process. The thermodynamic state, as I clearly told the before slide. Let me recall it. The collection of or collectivity of these variables like pressure, volume, temperature, okay. The example of state function is simply internal energy. Let us go to the path function. What is meant by path function? The thermodynamic parameter which depends thermodynamic process along with the initial and final state. Example, let us take simply the work done by the gas. We can clearly understand on the next. Okay, let me erase this on the next slides. Okay, work done by the gas. Let me take in container. I will place an piston above piston which is unmovable. I will place an piston which is movable. I will take in gas molecules. I'm taking randomly, since there is no distribution in it was not tightly binded like solids. Gases are lightly gases are tightly sorry. చెప్పురా బా ఏటి కనబడుతుంది నీకు ఇప్పుడు పైన ఏటి కనబడుతుంది పిస్టన్ అవన్నీ రాశాను ఇప్పుడు నీదిరా నేను చూడక్కర్లేదా ఇప్పుడు మళ్ళీ రాస్తానుండు okay, let us take a container and then piston in that which is movable. Let us take in gas molecules. We know that gas molecules loosely bind solid tightly bind. There is no uniformity in this distribution. Okay, let us take this. Due to some okay, let me give this with another color. Let us give it with pressure. It will move from the initial pressure to the final. Let us take this as V initial. It will take as V final. I will consider a small element dx. Okay, the force applied by gas on piston, I mean I'm telling this. We know that force equals to pressure into area. F equals to P into A. Let me take work done by the gas. W equals to integration of F into dx. F equals to PA into dx. Let me consider A. Let me take another color. Okay. This area as D, a small element of volume. Okay. Therefore, work done by the gas is W equals to V initial to V final P dV. Okay, most important form. Let us learn deeply in this slide. Okay, consider a graph in PV graph. Okay, let me take this pressure and volume this side. Let me take somewhat. We know that area is equals to P into dV is equals to work. Area under PV curve gives magnitude of work done by the gas. Simple. ఈ ఏరియా ఉందా, ఈ ఏరియా దీని వర్క్ డన్. ఈ వీళ్ళ ఏరియా అండర్ కర్వ్స్లో మనం నేర్చుకుని ఉంటాం. ఈ I will tell more clear. Let me take one. ఈ అక్కడ మనకి ఎంతైతే ఏరియా ఉందో ఈ ఏరియా యొక్క పీవీ కర్వ్ ఉందా, ఎంతైతే ఏరియా ఉందో అదే వర్క్. మనం మ్యాథమెటిక్స్లో ఏరియా అండర్ కర్వ్స్లో తెలుసుకుని ఉంటాం. సింపుల్. Okay, there is a doubt. What if gas expands and compressed? Take a value. Example. Expands, compressed. Let me give an neat visualization like above. PV graph. Let me take an volume of V initial and V final. Okay, this color was not visible. Let me take an color which can be visible here. Let me take an color red. I am taking an area of this. Since the work done is in from here initial to final, then work done is positive. Since Vf is greater than Vi, it's a positive graph. Let me take, since here I will take like in case 1. Here the gas was expanding. Let me take in case 2. Here the gas was compressing. P V. Let me take in V final here and V initial here. The direction like this here. Then the work done is negative since Vf is less than Vi. Okay, work done by a cyclic process. Let me take two graphs. Let me take in graph like let us take pressure and volume. V initial or let me take an end round cycle. Let us take in cycle process because the name itself tells us a process. Let me take in cyclic process A, B, C and D. Let us take the work done like this. Like let us take two work done here to understand this. Work done total is equals to work done W of ABC minus work done of CDA from CDA and ABC. Here we get two results. Let me take with another color. Let us take green. P and P. Let us take in circle of A to ABC like this. Here it's okay, from here the work done of ABC, the work done of CDA is like okay. Let me take another color to understand clearly. It's an cyclic process, clockwise cycle, anti-clockwise cycle. Here work done of ABC is positive, work done of CDA is negative. Therefore, work done of total cycle gives us the what? Area under the circle. Here gives us the results. Let us do a problem from the above. Let us solve together. For a given cyclic process, CAB as shown, it's an cyclic process. Anti-clock or clockwise. First, determine it's an clockwise direction. Let us take an graph, an empty slide. Let me take an black. Here we all know that work done of the cycle process gives by the area. Here area of a triangle of BH square, B 4 meter cube, H, okay, 5 pascals is the height, and the breadth from the figure here the height is sorry the height is 5 pascals and the length is 4 meter cube. From the figure we can show breadth is 4 pascals. Therefore height is 5 pascals. Substituting by, we get the work done of into 4 meter cube into 5 pascals. Pascals gives raised newtons per meter square. Newton per meter square. Meter square and 1 meter square cancel, and here we have to by the 1 meter, and these two cancel, and we get 10 joules. We know that it was in the clockwise direction and gives its positive sign, 10 joules or 10 mu. Okay, like this we can solve this question. And joules is answer. Okay, first understand, second graph, third sign, fourth applying formula, fifth required answer plus 4. Okay, let us come to the 0th. Let me take body B and body C. Let me take A and B contact with C. Here A contacted with B, A, B, C. Let me take with another. If A, B are in thermal equilibrium and B and C are thermal equilibrium, then we can say that A and C will also in thermal equilibrium. Like this. Let us consider a body B and body B and body C like this. We can say this. When A, B or come closest to the contact, A and B and C are in thermal equilibrium, then we can say that A and C are also in thermal equilibrium. Okay, let me clear here. It will also useful in our boards. I have forgotten to say that here Girotra tells about the principle of temperature. Therefore, TA is equals to TV is equals to TC. Let us take an enclosed vessel with an internal energy of UA and a small closed vessel UB. Let me take another color. Okay. We also see in violet filled with the containers in B. Therefore, we can say zeroth law. Ice at 0° Kelvin. Since energy transfer, energy flow from higher to lower, therefore here UA is less than UB and temperature of TA is less than temperature of B. Let us take an container. Let us take in gas molecules. Like I will color it with violet. let me take an measurement of temperature with thermometer. The amount of heat we get, the change in heat, and we get here the work done. Since the first law of thermodynamics states that the principle
Off.
law of conservation of energy let me take another one here. Energy neither created nor destroyed. But this also stated, but in isolated system the sum of all forms of energy constant. Okay. Therefore, del Q equals to amount of internal energy and change in work done. We know that del Q equals to heat supplied to the system work done by the system. Here, coming to the science convention, heat is supplied to the system is del Q gives us positive sign. Heat is extracted from system gives del Q is negative. Del Q coming out is negative, to the system is positive. Coming to the internal energy, let me take internal energy of system increases, gives del U positive. Internal of system decreases, del U is negative. Work is done by a system, del W gives positive. Work is done on the system, therefore del W gives negative. Let me write it clearly. Let me tell this. Find heat supplied to the, if its internal energy increased by 60 joules. Here the internal energy states that del U increased by is 60 joules and the work done 20 joules. Del what we have to find, del Q is equals to del Q equals to del U plus del W according to the first law of thermodynamics. Okay, let me write clear. Therefore del Q we have to find from 1 we get del Q equals to 60 plus 20 is equals to 80. Coming to the next question. The internal energy change in the system is observed 2 kilocalories. Okay, observe 2 calories. Here units is 1 calorie is equals to 4.2 joules. Let me understand through a diagram. like I'm shown that here the work done. Here the work done, del W is 500 joules and the heat is 2 kilocalories. These are the gas molecules and this is the temperature thermometer. I have kept this. Okay, we know from first law del Q equals to del U plus del W. 2 kilocalories is equals to del U plus 500 joules. Since we have to find the del U from this, del U equals 2 kilocalories minus 500 joules. 2 into 4.2 into 1 kilojoules is 1000 minus 500 joules. 8.4 into 10 to the power of 3 minus 500 joules. 8400 minus 500 gives us 7900 joules is our answer, required answer. Moving back to the next question. 110 of heat is added to a gaseous system. The change in internal energy is del U is equals to 40 joules. What is the del W? Is the question. We have to understand this. It was easy. From the first law, del Q equals to del U plus W. We know we have the question del Q equals to 110 joules equals to 40 joules plus del W. Del W is equals to 70 joules. Since it was work done by the gas, from I have told that in the sign conventions therefore the external work done equals to minus of work done by the gas. Since work done on the by the gas gives positive, since work done is positive, but the external work done is the negative of the gas, that is minus 70 joules. Okay, coming to the calorimeter. Let me take a container. I will take an Bunsen burner here. I want to heat this container. Del Q is equals to ms delta T. Therefore, S equals to del Q by m delta T. S gives us specific heat capacity. What is meant by specific heat capacity? For 1 gram 1 degree temperature increase, for 1 gram of solid or anything, how much temperature we have to increase for 1 degree Celsius temperature is known as specific heat. How much heat is required for the 1 gram to increase 1 degree temperature, 1 degree Celsius of the temperature scale is known as specific heat capacity. Okay, coming back to the molar heat capacity, let me take an example of first law of thermodynamics. Del W and the gas molecules, del Q. Del Q is equals to NC delta T. C is nothing but molar heat capacity. Okay. Molar heat capacity always depends on the process itself. Let me clearly explain in the next slide. Molar specific heat of for example, we have to take water is 1 calorie per gram degree centigrade. For 1 gram we have to take, for 1 degree centigrade we get specific. For m grams we require 1 degree centigrade. Let me clearly write it. Is ms. M grams at delta T degree centigrade gives us ms delta T. Similarly to the molar heat capacity, for 1 mole how much degree centigrade we have to increase is known as molar heat capacity. For n mole 1 degree centigrade is Nc. For n mole at change in temperature gives us Nc delta T. Therefore del Q equals to Nc delta T. Therefore S equals to specific heat. Del Q is equals to ms delta T. It will be more useful in the table which I have discussed in that. Okay, coming to the thermodynamic process. What is meant by thermodynamic process? thermodynamic process is the change of system from one thermodynamic state to another, from one thermodynamic state another is known as thermodynamic process. Basically, thermodynamic process is broadly divided into 5 types. Let us take this. Let me take in color of violet. Okay. Okay. Let me write it clearly. Isochoric isobaric process, isothermal process, adiabatic process, and last but not least, polytropic process. Let us discuss neatly in the next slides. Coming to the isochoric process. Isochoric process, we know that volume is constant. In a closed container, let me take an color and let me draw it. Gives us del Q, and these are the molecules itself. We know that del Q equals to heat supply to the system. Therefore, del U equals to a 10 moles NFRT by 2 is equals to we know that FR by 2 gives C N CV del T. Let us derive this. Del Q equals to del U plus del W. Del Q is equals to NFRT by 2 plus work done. There is no work done. 0. Q equals to NCV into del T is equals to NFR delta T by 2. N delta T cut cut. Therefore CV equals to N R by 2. CV is nothing but molar heat capacity at constant volume. Graphs of isochoric process. Let me take P versus V. V. Since volume is constant, we get a straight line here. Let me take pressure versus temperature graph. We get a straight line. Since PV equals to nRT, volume is constant, pressure is directly proportional to temperature, and the slope tan theta is equals to nr by P. Since volume is constant in isochoric process, let us take volume versus temperature graph. Since volume is constant, we get a graph like this. As technique. Given the graphs of what is meant by isobaric process. Simply in the states of matter we know this as Charles' law. In Charles' law we know that pressure is constant. Let us take an example like this. Let me take an container. Let me take an open vessel like this and then work done. Del W and then heat here and then gas molecules. Here we get del U. Therefore, del U equals to NFRT by 2 is equals to NCV into delta T. Del W is equals to integration of PdV gives, since pressure is constant, we get outside P into D. Therefore, del W equals to NR delta T. Since PV equals to nRT, pressure is constant, V equals to nRT. Therefore, del V equals to nR delta T. Therefore, we know from that first law of thermodynamics, del U plus del W, first law, NCP into delta T is equals to NFR delta T by 2 plus NFR, sorry, NR delta T, some at some work we get 2. N delta T will be cancelled at both the sides. Therefore, Cp is equals to Fr by 2 plus R. Cp equals to Cv plus R. Molar heat capacity at constant press. Coming to the let me take pressure versus volume. We get in straight line. Pressure value versus temperature. Again we get a straight line. Let us take volume versus temperature. We get in straight line since PV equals to nRT. P is directly proportional to T. Therefore, V and T, we get 10 temperature like this, V1 and V2. Coming to the isothermal process, here temperature is constant, like boils let me take an hello. Okay, let's back to our last lecture. I have stopped from the isobaric. I have to start from the isothermal. Sorry. Yeah, am I audible? Okay, let's go to the isothermal, which is temperature constant. It's also from the states of matter we can know Boyle's law. Let me take in an open container. Within work done, within gas molecules surrounding by it, and this will be our heat, and this will be our internal energy. Let me change the color. This is a diathermic fall. Okay, we know that internal energy equals to NFRT by 2 from the previous lecture. Sorry, del T is 0 since temperature tends to 0. Del U is equals to NFR del T by 2. Here T tends to 0. This whole becomes 0. Now coming back to the derivation part. The work done in this process del W equals to PdV. From ideal gas equation, PV is equals to nRT. P equals to nRT by V. Okay, substituting in this we get nRT by V into dV from initial volume to final volume. Del W equals to nRT naught. It is a constant we can take from this V initial to V final dV upon V. 1 by V is ln of V is equals to nRT naught ln of V final by V initial. Since PV is equals to nRT, here nRT can be replaced by PV. From this we can write PV P initial V initial ln of Vf by Vi is our required. Therefore, from first law of thermodynamics, del U plus del W is equals to del Q equals to nRT naught of ln of Vf by Vi. Let me take the color. From we can state that del Q is equals to NCT delta T, molar specific heat capacity at constant temperature. CT is equals to del Q by N delta T. Temperature tends to 0. From this we can say CT is infinity. CT tending to infinity. Therefore, from coming back to the graphs, PV graph, let us take. It will be n, since PV equals to nRT, P is inversely proportional to volume. Therefore, it will give an hyperbola. Let me take another graph, PT. PT gives a straight line since temperature is constant. Similarly, VT gives us a straight line since temperature will be constant. Okay, these three graphs are important. These are the results. And coming back to the adiabatic process, since there is no heat flow, del Q tends to 0. Let me take in two non-conducting walls as an example. Sorry for the diagram. These are non-conducting walls. This here will be a work done, and this will be our gas molecules. There is no heat flow. No heat flow. Remember it. From internal energy, we can say that del U equals to NFR delta T upon 2. Del W equals to PdV. Therefore, del Q is equals to del U plus del W. Del Q tends to 0 since there is no heat flow. NFRT upon 2 plus del W. Therefore, del W equals to minus of NFRT upon 2. From this, here we can write del Q is equals to NC Let me write adiabatic into del T. Since del Q tends to 0 is equals to NC adiabatic. In a short notation I am writing adiabatic. Therefore C adiabatic is equals to 0. In previous isothermal process, Ct tends to infinity. Here C adiabatic gives 0. Okay. These are the non-conducting walls. There is no heat flow. Let me do a derivation. To get the adiabatic exponent, we know that from ideal gas equation. Let me write it neatly. We know that from ideal gas equation, PV is equals to nRT. PTV is equals to minus NFRT upon 2. Don't confuse here. I am writing del W instead of this. Simply from the previous slide. Here I am giving this as PdV gives negative of NFRT upon 2. Okay, let me take as a second equation and this as a first equation. Substituting from 1, P is equals to nRT upon V. Keeping this in 2, we obtain nRT upon V into dV gives us minus NFRT upon 2. Equating from this I can cut this. Okay, let me give it another one. I will cut NRT. Here we get dt. Let me take the color. From this we can say integrating on the both sides with the volume V initial and V final gives us the remaining derivation. Integration of F by 2 is a constant here. Air temperature will be the key rho. T initial sorry T initial, T final, dt upon T minus F by 2 is constant here. Therefore ln of V final by V initial gives us minus F by 2 into ln of T2 upon T1. Ln of Vf by Vi. Here it will go to the exponential of this. Ln of T2 upon T1 over minus F by 2. Ln of Vf by Vi is equals to ln of T2 upon T1 upon minus F by 2. Here we can cancel these both. Coming to the next slide. Vf by Vi is equals to T initial by T final to the power of positive F by 2. Since I am interchanging initial and final from this we can say Vf into Tf to the power of F by 2 is equals to V initial into T initial to the power of F by 2 gives us constant. Since Vt to the power of F by 2 gives us constant, let me erase this. It will be more understandable in our PYQs. Let me say the concept here. Therefore, V into PV upon NR to the power of F by 2 gives us constant. I am not done anything. PV is equals to nRT. Therefore, T gives me PV upon nR. I am substituting here. That's it. From this we can say V to the power of F by 2 and V to the power of 1 plus F by 2 gives us constant. Therefore, substituting V 1 plus F by 2 over Fr by 2 is equals to constant. Let me give you an idea. 1 plus F by 2 into R gives me Cp. 1 F R upon 2 gives me Cv. Therefore, Pv to the power of Cp upon Cv is constant. Pv to the power of adiabatic exponent gives me constant. Result. Since gamma is nothing but adiabatic exponent. Okay. Let me explain you more detail in our PYQs. Let me tell you that equation for adiabatic process. Pv to the power gamma is equals to constant. Since from the ideal gas equation Pv equals to nRT, P gives me, sorry, let me erase this. Sorry. PV is equals to nRT. Therefore, P gives me nRT upon V. Substituting here, we get nRT upon V into V to the power of gamma gives me constant. Therefore, T into, sorry. Let me write it clearly for the equation. Adiabatic process. From the above result, we know that PV to the power of adiabatic exponent gives me a constant value. Therefore, from ideal gas equation, PV is equals to nRT. P gives me nRT upon V. Substituting here, let me give it V1. This has 2. Substituting 2 in 1, we get nRT upon V into V to the power of adiabatic exponent gives me a constant value. Therefore, T into V to the power of gamma minus 1 gives me a constant value. Okay, this will be our result, most important result. Let me tell you another result. P into T by P to the power of gamma. Gamma means nothing but adiabatic exponent gives me a constant value. P to the power of 1 minus R into T to the power of R. Let me write it clearly. T to the power of 1 minus R into T to the power of R, adiabatic constant, exponent give me constant. Therefore, P to the power of P into T, let me write it clearly here. These are the most important results for our questions in our JEE mains and NEET. P T to the power of gamma by gamma minus 1 gives me an constant value. Therefore, result 1 and result 2. Let me highlight this. And this too. Let me write it. Result 1. Result 2. Most important. Let me write it. Coming back to the graphs, these plays an important role in our physics. Let me give a graphs of PV, PT and VT. Coming to the PV graph, let me draw. These were the result, that's why I am highlighting you this. Gives me an hyperbola. Since PV to the power of adiabatic constant gives me adiabatic exponent gives me a constant, P is equals to constant upon V to the power of adiabatic exponent gives us an hyperbola. Let me give, and then let us take PT graph. Let me take and the color to this. This gives me, first I will tell you from the result to P into T to the power of gamma by 1 minus gamma gives me in constant. P is equals to constant upon T to the power of gamma by 1 minus gamma. Therefore, this gives me constant into T to the power of gamma by gamma minus 1. Since I am changing the negative side, 1 minus r 1 minus adiabatic exponent to the r by adiabatic exponent minus 1. Therefore, this is an positive value. Note. That's why this graph keeps on increasing this way. Okay, let me draw neatly. Let me take this color. Okay, for VT graph, the result will be as like this. From result 1, TV to the power of gamma minus 1 gives me n constant. V into T to the power of 1 by 1 minus gamma adiabatic exponent minus 1 gives me V to the constant by T to the power of 1 minus gamma minus 1 gives me an exponentially decreasing function like this. It will be gradually decrease like this. Okay, these are the three graphs to be seen very well. Okay, let me go to the let me tell the different results of graphs of adiabatic and isothermal process. For this, I'm taking the similar graphs as like the previous for the adiabatic process. Let me take this. Since I am telling this because more questions asked me these variation types. Let me take PV graph, PV graph, and PV graph. Let me pick this. Since isothermal graph is always sharp, since sharp means isothermal, these graphs are too sharp. And let me give a color to the isothermal. Isothermal graphs will be increasing like this. Sorry. Like this. Okay. Sorry. This is adiabatic. Sorry, let me explain you clearly with another color. Let me take green. Since blue line gives me adiabatic result. Since adiabatic graph gives us sharp graph, since it will be our adiabatic, and this will be our isothermal. Sorry, I am confused here. This graph gives us adiabatic, and this graph, sorry, let me give it another color. Sorry for the late. This will be a lag to you. Let me explain you clearly, that's why I'm taking this much time to understand you. Let me take an isothermal graph like this. This was isothermal. Let me take another color. I will choose this color to the adiabatic. And adiabatic graphs are too short. This will be our adiabatic, since these graphs are very short. Like this, we can share this. Let me take this as a point. This and this. This is isothermal, and this is adiabatic. Since these graphs are very short and from this was very not sharp line adiabatic. This we can say that this was an isothermal graph, and this shows as adiabatic. Since adiabatic was more steeper, that is sharp than isothermal. Okay, do you understand? These are the most asked results in JEE mains and NEET. Okay, let me erase this. Okay, coming back to the last one, isotopic process. Isotropic process is nothing but PV to the power of beta gives us n constant value. Therefore, let me derive this through n. Let me give me a color to this polytropic. This was very interesting process. From sorry del u equals to nf r delta t upon 2. Del w gives me an PdV work done from V initial to Vf constant upon V to the power of Vn. Since polytropic is nothing but PV to the power of eta gives me an constant into dV. By substituting it, let me take this here, constant into V minus n plus 1 by V minus n plus 1. Since integration of V to the power of n is nothing but V to the power of n plus 1 by n plus 1. Basic formula. From this we can derive this constant upon here we forgot to write V final and V initial. Constant upon, I am changing this in interchanging this, I get 1 minus eta into Vf 1 minus n minus V initial 1 minus eta. This gives me 1 by 1 minus eta into Vf constant upon V to the power of n. Vf into 1 minus n is nothing but Vf into 1 by Vf to the power of V. I will clearly explain this. sorry. V to the power of 1 minus eta gives us V into V to the power of 1 minus V1, V by V to the power of n. By simply substituting like this, in this we get minus V initial into constant upon V to the power of n. From this we get del W is equals to 1 by 1 minus eta into Vf minus Vi Pi. Since from this therefore let me write it very neatly. Pf minus Vin is nothing but n delta T upon 1 minus eta gives us del work done, change in work done by the gas in this process. Therefore let me take another color, violet. Substituting in this, del Q equals to del U plus del W from first law of thermodynamics. Substituting these all values 1 and 2, sorry, I mean this as 2, we get NC delta T gives us NC delta T gives me NFR delta T upon 2 plus NR delta T to the power of 1 minus eta gives me N delta T, N delta T, N and delta T will be cancelled. From this we can write C is equals to Fr upon 2 plus R upon 1 minus eta. From this we can write Fr upon 2 minus R by eta minus 1. Therefore we can write this as C is equals to let me take in blank. Okay, let me write as Fr by 2 can be written like this. Fr upon 2 is nothing but gamma equals to 1 by 2 by F is nothing but gamma minus 1. Therefore F by 2 gives me 1 by gamma minus 1. Therefore here F by 2 into gamma minus F by 2 can be replaced by adiabatic exponent minus 1. Therefore substituting here we get R upon gamma minus 1 minus R upon eta minus 1. Most important, therefore let us try this question. The given diagram shows us 4 processes. One is isochoric and isobaric, isothermal and adiabatic. The correct assignment of this process is in the same orders given by DACB, ADCB and something. From this graph I have said earlier, very short means adiabatic. Less steeper than, less short than adiabatic gives us isothermal, and this gives me isobaric, and this gives me isochoric. Since I have explained you in this, in isochoric volume was constant, therefore since in isochoric volume is constant, since it gives me a straight line here, this gives me a straight line here, and this here in isobaric pressure is constant, therefore it gives a straight line as a result. From this we can clearly say that the correct let me tell adiabatic 2 very short than isothermal. Isochoric gives me D, isobaric A, isothermal B, and adiabatic C. Therefore D A B C D A C D E, and this gives me an answer option. This was the 8th April shift 2 question. And coming back to this, let me change color. A gas can be taken from A to B via two different processes A, C, B. Let me take an arrows A, C, B and A, D, B. A, C, B and A, D, B. Let me take like this, and this will be grows like this. When path ACB is used, the heat taken by the path is 60 joules into the system and 30 joules of the work done. Del W gives me 30 joules. From first law we can clearly say that del U equals to del Q minus del W. Del Q gives me 60 minus 30 gives us 30. Sorry, collided like this. Gives us 30 joules. From, let me take another color A, D, B path. Path ACB and path ADB, and this path goes like this. This was a cycle process. If ADB is used, work done is 10 joules. Del W gives me 10 joules, and done by the system, and heat gives me 30 joules from this path. From A C B path gives me heat flow. Del Q equals to del U plus del W gives me 30 joules plus 10 joules gives me 40 joules is our answer. Okay, and this will be our integer type question. 64 oxygen is expanded. Oxygen is expanded under constant pressure of 5 atm pressure. This will be our pressure, and at constant pressure, if temperature of gas is increased by 200 Kelvin, find heat supplied. Del Q is how much. Also find increased volume of the gas. Therefore, it was given oxygen. Oxygen is an diatomic gas. At constant pressure gives me isobaric. Therefore, the degree of freedom is 5 for the at normal temperature. And here del T was given. We have to find del Q and the volume of the gas. Therefore, we have to find del Q. Del Q gives me del U plus del W gives us NFRT upon 2 plus NR delta T. And gives me from isobaric process we get NCP delta T. Cp is nothing but Cv plus R. Substituting here N into Cp plus sorry Cp is equals to Cv plus R N into Cv plus R into delta T. N into Fr upon 2 plus R into delta T gives me 2 in. Okay, let us find number of moles here. Number of moles is nothing but moles upon molar mass. Molecular mass is nothing but given 64 grams upon oxygen is nothing but O2. 2 into 16 gives me 32. It gives me 2 moles. N equals to 2. Therefore, two into F, degree of freedom is nothing but 5 into R by 2 plus R. Sorry. 2 into F R upon 2 plus R into delta T. 2 into F R by 2 plus R into delta T. 2 into 7 R by 2 into delta T is nothing but 200 kelvins. Gives me 2 into 100. 7 to 14, 14 into 100, 1400 joules. answer. Like this we can solve this. First the given we have to understand here. We have to find the number of moles, and substituting here it will not mention isobaric, isochoric, adiabatic or polytropic. We have to understand the terminology: constant temperature, constant pressure, constant volume. By this we have to obtain which will be the process in the required question. Go by going to the next question. 5. Okay. వస్తుంది చేస్తాను. Okay, let's solve this question. 5 kilomoles of oxygen is heated at the constant pressure is nothing but isobaric. The same question here repeated. Isobaric pressure, the temperature of the oxygen gas is increased from 295 to 305 Kelvin. The molar heat capacity of the oxygen at constant pressure. The molar heat of oxygen is at constant pressure. The amount of heat absorbed in kilocalories is. We know that Qp is at constant pressure. Molar heat capacity gives me NCP into del T, where N is the number of moles. Molar heat capacity. Here the number of moles is given. N equals to 5. 5 kilomole. Sorry, I will write it clearly. Sorry. Kilomoles into something. The constant pressure is 6.994 kilocalories kilomole Kelvin into the temperature T2 minus T1 gives me 305 minus 295. Therefore QP is equals to 5 kilomole into kilocalories by kilomole into Kelvin. Kilomole cancel. 6.994 into Newton something gives me an required answer. Okay, solve it by yourself. Here the initial and final, we have to consider the initial and final states. The figure shows two processes A and B. If QA and the change in heat of A, change in heat in B are the amount of heat absorbed by the system in two cases, del UA and del UB. The internal energy of A and the internal energy of B are changes in the internal energies respectively. Then states, okay, del UA is equals to del UB. There is no change in this. Since work done during process of A is greater than process B, from first law of thermodynamics, del Q is equals to del U plus del W gives me del QA is greater than del QB. Therefore del QA and del QB in del UA is equals to UB. Therefore option D is our answer. Since I have told you earlier, del Q increases, the work done also increases. Therefore del W is also del B also increases, like heat increases. Since del Q increases, del W also increases. Like this we can say. Moving back to the next question. Going back to the mixture of gases. Mixture of gases is nothing but let me take an closed container. Audible? Sorry for the inconvenience caused. Let me take an container filled with number of gases, molecules. Let me take an molecules like yellow, let me take another color, let me take another color. Mixture of gases is nothing but degree of freedom of mixture is N1 F1 N2 F2 plus so on upon N1 plus N2 plus so on. Every molecule N1 is nothing but number of moles of first molecule, and F1 is nothing but degree of freedom. Therefore, Cp gives me from the above Cp is nothing but R plus F by 2 into R. For every mole it has each degree of freedom. Cp is nothing but F mixture into R upon 2 plus R. Cv is nothing but F mixture into R upon 2. Therefore, adiabatic exponent Cv upon Cp. Let us solve the first table I have left. Where I have. Okay, let us solve this table. Cv is nothing but F by 2 into R. Therefore, 3R upon 2 and 5R upon 2, 7R upon 2, 5R upon 2, 6R upon 2. Cp is nothing but Fr upon 2 plus R. 3R upon 2 plus R gives us 5R upon 2. 5R upon 2 plus R gives us 7R by 2, 9R by 2 and 7R by 2. 7R by 2, it's 8R upon 2. Therefore, adiabatic exponent gives me Cp upon Cv. Gives us 5 upon 3, 5 upon 3, 7 by 5 and 9 by 7. It gives me 7 upon 5 and 8 by 4. Okay, sorry. A small calculation mistake. 8 by 6, 2 3 is 6, 2 4 is 8, gives us 4 upon 3. Okay, like this we have to solve the table. Okay, The bulk modulus of a gas we have studied earlier in our classes. Mechanical properties of solids. Del P is nothing but, sorry, I have erased this. Del P is equals to minus B into del V by V. Remember this. For isothermal process, what will be the constant? For isothermal process, we know that temperature is constant. Therefore, PV is equals to constant and del P into V differential. Okay, sorry. Let us solve this by this. From this we get like del P into V plus P del V is equals to 0. Therefore del P is equals to minus P del V upon V. From this both are similar. Do you understand the concept? Form B isothermal is equals to adiabatic constant. We know that PV to the power of exponential adiabatic exponent gives me a constant del P into V to the power of adiabatic exponent plus P into gamma into V to the power of gamma minus 1 into del V is equals to 0. Del P into V to the power of gamma is equals to minus gamma into P V to the power of gamma minus 1 into del V. Therefore del P is equals to minus gamma into P to the power of V minus gamma minus 1 by here we obtain V to the power of gamma into del V. Here will be cancelled. From this del P is equals to minus adiabatic exponent into pressure into del V upon P. Therefore from this result we get del P. B bulk isot bulk adiabatic gives us gamma P, since B minus B into del V upon V gives us del P, bulk modulus. since polytropic. Moving on to the polytropic, we get PV to the power of eta gives us n constant. Therefore, P polytropic gives eta into P. Therefore, let me write all here once. Isochoric, isobaric, isothermal, adiabatic. Here eta tends to infinity and eta is equals to 0, eta equals to 1, eta equals to adiabatic exponent. B is equals to infinity, B equals to 0, B equals to P, B is equals to gamma P. Therefore, free expansion is nothing but let me take in container which is in place between the piston. Here it is filled with air. And these gases tries to gives a pressure to this. Here there is no work done. A free expansion law work done is 0. The work done is 0. Coming to the quasi-static process. Here the system is remains in internal thermodynamic equilibrium. Quasi-static means almost static. Extremely slow process. All reversible process are quasi-static. since rate of change system is negligible. Infinitely small rate since rate of change of system is low. Intermediate state. Here thermodynamic equilibrium is attained all the time. Let me take this. Let me 12. Right. Quasi static. Work done. Let me write quasi-static work. For isothermal process, we know that temperature is 0. Therefore, temperature is constant for whole process. W equals to mRT ln of Tf by T initial. Isobaric process. The pressure is 0. Here pressure is constant, therefore W equals to P into Vf minus V initial. Ignore this because it is for JEE advanced. For isochloric process, volume 0 and constant, therefore there is no work done and it's 0 complete. Let me tell the indicator diagram. The indicator diagram is nothing. The indicate is diagram nothing but the indicate thermodynamic state of the gas. of a system. Sorry, this color doesn't match this. It's dynamic state of an system. It nothing but it indicates the thermodynamic state of a system. That's here. Three different processes that can occur in an ideal monoatomic gas. Monoatomic gas is nothing but single, shown in the figure P versus V graph. The paths is labeled as AB, the AB, AC, and AD. The change in internal energy during this process are taken as internal energies are taken as EAC and EAB. Okay, the work done is taken as WAB, WAC and WAD, and the correct relation between the parameters. This is the question of JEE mains 5th September 2020 question. It's a monoatomic gas. It's nothing but TB is equals to TC is equals to TD. Del T is equals to del T of AB is equals to del T of AC is equals to del T of AD. So here temperature 1 is greater than temperature 2. Monoatomic gas here the only monoatomic ideal gas is helium, neon and argon. Translation kinetic energy. Therefore average kinetic energy is equals to 3/2 of kT. Therefore EAB is equals to EAC is equals to EAD. Since we apply the formula del U equals to NFR upon 2 TF minus T initial, W is equals to P del V. From here we can see from A to B the volume was increasing. Therefore WAB is also something is greater than or 0. From AC volume is constant. Therefore WAC is equals to 0. From A to D gives us volume decreases. Therefore WAD is less than 0. Since WAB is increases, therefore WAB is greater than 0. From AC, volume is constant, therefore volume AC is equals to 0. Its decreasing is less than 0. Simply A equals TB, C equals to 0 and AD is less than. Option A is the correct answer. Okay, like this we have to understand the graph. Let us take conversions of graphs. These are nothing. Let me take a graph similar to this. Let me take P versus V graph. 2P and P now. T naught, 2T naught, 4T naught. Sorry, I am taking PD graph. Therefore, I am taking and let me take this graph from here to here. Sorry. From here to here I will mention A and B. Let me take another one. I am going from this path C. Therefore we can attain here and C to the return position like this. Therefore it's a cyclic process here. Therefore we know that P is directly proportional to V. PV inverse is equals to constant something. Therefore P into T by P of inverse is equals to constant. Therefore P is directly proportional to the square root of temperature. Therefore from this we can say that it was polytropic. This as isobaric. Since pressure constant in isobaric, in isochoric we know that in isobaric pressure was constant, in isochoric volume is constant. Here isochoric volume is constant. In polytropic it will be like this temperature, therefore like this. Okay, T0 to T0 something for T0 as you mentioned here. Okay, like this we have to understand these graphs. Let me go to the question. Which of the following equivalent cyclic process corresponding to thermodynamics is in 1 to 2 is an adiabatic? Okay, here volume is constant, therefore it was like isomeric here, since pressure was constant. Here take this as isobaric, and this is and this. Okay, in adiabatic process, here volume, sorry, this was not this will be our answer. Since here volume is directly proportional to the temperature, I will give you this as a homework. Give me an explanation. Let me know how many can do. Here from the VT curve I am taking and the one color. Okay, let me take this graph. Let me draw the similar values. T0, sorry, let me T0 2 T0 6 T0 and 3 T0. T0 2 T0 3 T0 and 6 T0. Graph was volume versus time. Okay, and 2 V0 here and V0 here. Here let me take from here, let us consider A, from A to here B, and let me consider another color, suppose green. A to B and B to C, and let me take another color and we reach from C to D, and these both coming to the 0 and meeting at the point from A, B and C, returning to their original path, original point. Sorry, let me write. Okay, from this we can say that volume is directly proportional to the temperature, since this can be seen as isobaric. Since I have explained this here, volume is directly proportional to temperature. This was isobaric and this was isochoric. Since in isochoric, volume is constant. In this is also an isobaric, since volume is directly proportional to temperature. An adiabatic process, the density of an diatomic gas becomes 32 times of the initial value. The final pressure of the gas is found to be n times of the initial value. The value of n is, let us consider the density, okay, diatomic gas. Thirty-two times of an initial value, rho equals to mass upon volume. Upon 32 gives us our required answer. Let me solve this. PV2 over gamma is equals to constant in adiabatic process. Since I have to find the adiabatic exponent, 1 plus 2 by f is equals to 1 by 2 upon, there are 5 in this at normal temperature gives me 7 upon 5. Okay, P naught, let me consider P naught V naught to the power of 7 upon 5 is equals to constant. P into V naught upon 32 gives me 7 by 5 is equals to constant. Okay, 32 can be write 2 to the power of 5. P into V naught upon 7 by 5, 2 by, sorry, two to the power of 5. This by can be cancelled, some value we can get answer. By this we can do. Okay, 1 mole of an ideal monoatomic gas, is compressed isothermally in a rigid vessel to double the pressure at the room temperature 27 degrees centigrade. Let me give this as an homework. This can be done like this: nRT of ln V final by V initial. Let me do this as DIY. Do it yourself. Okay, coming back to this question, let me give another color to this. Two moles of helium gas, n equals 2 of a helium gas. Helium gas is nothing but helium is nothing but monoatomic gas are taken by a cycle A B C D A n cyclic process of PT graph. Assume that gas is work done from A to B. What is the work done in this? We know that NR into delta T is equals to work done. Okay, work done on the gas will be positive. Okay, n is given, n is 2 into R equals to 8.314 kilocalories per mole. Something we can write as R into delta T. (500 minus 300 kelvins gives us 200 kelvins as change in temperature into 200 gives me 400 R. Since this is isobaric process, since V is directly proportional to temperature. Therefore, this will be given our answer. Therefore, work done equals to 400 R is our answer. Okay, coming to the second law of thermodynamics. Simply, the second law of thermodynamics tells about the spontaneity. Spontaneous of a process. Here there are two statements. One is Kelvin Planck's and Clausius statement. According to Kelvin statements, efficiency can't be done 100%. Sorry. %, efficient energy is not possible here. According to Clausius statement, no process is possible when the transfer of heat. No possible sorry, I am writing a wrong statement. He states that no process is possible here when heat transfer from a colder to hotter object according to Clausius and Kelvin Planck's. Let me tell you by an example. Let us take an hot tea in this. Here internal energy is in this. Sorry. Assume there is a tea here. Sorry, hot tea. Here, the change in internal energy and change in heat. Therefore, del specific heat is decreases here is equals to minus Q of T1. Since del S increases, temperature decreases. Del S decreases, temperature increases. Therefore, Q is equals to del U. Here, let us take T1 as the temperature here and the T2 is the temperature outside. Therefore, T1 is greater than T2. Since yes, del S2 increases, minus Q upon T2 decreases. Del S2 increases, temperature decreases. This is known as spontaneous process. Example of non-spontaneous is tea. Therefore, here we get del Q from the outside of the T2. Here in T, the del Q is like this, since it was non-spontaneous. Here, spontaneous occurred naturally. We here in spontaneous if it started, it goes on continuously. No need of energy, as in input. Therefore, the difference between the spontaneous and non-spontaneous. Therefore, from this, del S1 plus del S2 gives us minus Q upon T1 plus Q upon T2. Here temperature decreases, therefore we will get a positive sign here. Therefore Q into 1 by T2 minus 1 by T. Therefore S total gives us greater than 0, therefore it was spontaneous process. Therefore coming back to the last concept of this thermodynamics, heat engine. Heat engine is nothing but which works on Carnot cycle. Let us say source as T1 let me take as sink as T2. Therefore we will get 10 work done. Systematic. Therefore T1 is greater than T2. Eta equals to W by Q1. Q1 minus Q2 by Q1 gives us eta equals to 1 minus Q2 upon Q1. Therefore, eta maximum is equals to 1 minus, we will get Q2 by Q1 is like this. For maximum efficiency, work done is maximum, Q2 is minimum. Therefore del S net is 0. Del S1 plus del S2 is equals to 0 minus Q upon T1 plus Q2 upon T2 is equals to 0. Therefore Q1 by T1 is equals to Q2 by T2. Q1 by Q2 is equals to T2 upon T1. Therefore Q2 by Q1 is replaced as T2 upon T. Okay, let me tell about heat engine. Heat engine is nothing but a continuously operating device. A continuously operating device produces work from by transferring heat from heat source that is high temperature to a heat sink low temperature. Using a working fluid. Since it was nothing but Carnot engine in simple words. Okay, this was clear or not? Tell me in the comment sections if any doubt arises. Okay, coming back to the last and final concept of this lecture, let me take blue. Since let us take an reversible process. Reversible process is nothing but it can return to the original states without or with no other change anywhere in the surroundings. Let me take an system in the surroundings here. This is no system plus surroundings. Sorry, I was mistakenly written here as a surroundings. In the universe, system plus surroundings is known as universe in this thermodynamics. Let me take a container. Let me take in gas molecules. Since del S is 0, therefore this is extremely slow, that is system plus surroundings, that is quasi-static, as I told before. Irreversible is nothing but del S is greater than 0, and this is extremely fast. Okay, done with the lecture. Let me tell I have forgotten to say that the first law of thermodynamics very clearly. Let me tell. Sorry. First law of thermodynamics is nothing but law of conservation of energy. The summation of work done of the whole cycle gives us summation of heat done by the cycle. I mean, the algebraic sum of all energies transfer across system boundaries is 0. Therefore, net energy transfer Q minus W is stored in the system itself. Let me take in color. Let me finish this as soon as possible. Q minus W is equals to del E. Therefore, Q is equals to del E plus W. Let me thin this. Sorry. Therefore, del E plus W equals to Q. Let me take a system, a rigid system. Let me take sorry let me take Q1, Q2, Q3 and work done of 2, work done of 1, work done of 3, work done of 4. Therefore, the final conclusion, Q1 plus Q2 minus Q3 is equals to del E plus W2 plus W3 minus W1 minus W4. Thank you. See you in the next lecture. Bye.